it's all sounds so fantastic in theory, but we seem such a long way away. So why are we even talking about applications at this point?
I think it's because the applications are meaningful, and again, this goes back to Professor Feynman. Why did he suggest quantum computation? Because we needed to, and we continue to need to understand the behavior of systems that exhibit quantum mechanical behavior. That is just so fundamental to understanding, to harness material science, to harness matter and energy down at that molecular level. Wouldn't it be great if we had a machine that we could flip a switch and it turned carbon dioxide in the atmosphere or methane in the atmosphere into something that was like a little diamond? Wouldn't that be great? CO2 in, oxygen out, diamonds drop out the bottom. Manipulating and having that with energy we could afford, to have it be something that we can afford the energy going in. Well, that means if you understood the material science down to that subatomic level, the realm of quantum mechanics, you might actually be able to design and engineer a system that does exactly that. Now, that is complete science fiction, but you will commonly hear, carbon's precipitator, mentioned as one of the potential, things that you could do if you had this capability. Again, we look at the photosynthesis in plants, and we see it's so efficient and it's so cheap that literally sprouts out like weeds. And weeds in my garden do a better job of harnessing light from the sun than all of the engineered panels on my roof. Wouldn't it be great if we had systems that we engineered for purpose that could do the same thing? So back to Professor Feynman, he pointed us in this direction because he believed in the ability of humans to utilize this capability if we move this into an engineering tool, if we had this ability to manipulate and understand, simulate, adjust, engineer systems on the quantum mechanical scale, then he saw great promise there, and I would agree. And so that's why you add that first impetus. Then we add in the fact that now we also believe that this can be applied to massive logistics problems, that this could be applied to machine learning. Well, let's just say machine learning, but really, general artificial intelligence problems. So tremendous capability there in both symbolic problems and quantum mechanical behavior problems. That's why people are so interested in the technology. It has that promise, but we always have to be careful, have to be cautious, because yes, if you had infinite funds, doubling down on every bet will eventually you'll win. But that kind of a betting strategy only works if you have an infinitely deep pocket, and also it only works if the casino also has infinite monies that they can put into it. So that's not a realistic betting strategy. That's not one that we can afford. So we want to be realistic. We don't want to be pessimistic. We don't want to be optimistic. We want to be realistic. What is it going to take? And as we look at the technology and the successes we've had so far, which are promising, as something becomes more promising, then it also should invite greater scrutiny, greater collaboration to say, okay, well, I see you got 5 qubits, and I can see now you're going to have 100. Okay, let's take the next step. Let's figure out if you could take 100 and make it 1,000. If you could take 100 and make it 100,000, what are the ramifications? Can we work out the engineering around, so we can understand, and we won't invest in realizing 100,000 qubits and then find, oh shoot, turns out we don't have enough energy in order to run this system. Turns out that we don't have enough of this rare earth material. We don't want to find out after the fact that our technology has a limiter that we did not understand, not because we couldn't understand it, but that we weren't having that part of the conversation yet.